That's okay. Okay, so this is listed as a program talk, but it's really just for culture. It will not be on the final exam, the final program exam. You didn't know we had those, did you? But the NSF requires it. Anyway, so I've planned what's not an especially long talk, expecting that there'll be some discussion. So I'm not planning to go into every subtlety of this subject and all of the responses, such as Hawking's response from yesterday, but just the overview. There's some experts here. Also, the A from AM Salmeri is here. The M should be arriving, making a grand entrance soon, I assume, and other experts, Andrea and Steve. It's not the people out in the crowd; they're around. Anyway, so what I want to do first is to review the information problem. Then the firewall argument. And then some responses, most particularly the one that seems to, well, A, get the most attention, and B, most closely resonate with things from quantum field theory, is this ER equals EPR. And so first to review first of all Hawking radiation. So I'm going to draw the near horizon region in ingoing Eddington-Finkelstein coordinates. The coordinates aren't important, but I find these very intuitive for this problem. So the horizon is vertical, and ingoing light rays just go in. And outgoing light rays, well, the horizon is a null ray, so this is out. If you start a little bit outside of that, you peel off and eventually make it to infinity. If you start a little bit inside of that, you peel off and eventually get to singularity. Another way to think about these coordinates is these are coordinates in which the light cones tip over. If you're inside, then the light cone is fully tipped over and both rays are ingoing. If you're outside, one is going in and one is going out. And now to review this sort of the simplest, most robust version of the calculation of Hawking radiation, I want to think about so the asymptotic observers out here. I want to think about wave packets that initially are that end up far away, and let's suppose they're fairly narrow. Don't have to be, but just for the sake of imagination, reasonably narrow in terms of the frequency as seen by the asymptotic observer. So this outgoing Hawking wave packet I'll call B, and because if I was being more thorough, I would put an index on there and imagine a complete set of these packets, but to keep the notation simple, just call it B. And you'll notice, of course, as you follow B backwards, the wave packet never gets behind the horizon because it is a horizon. And so if we want to quantize a field in this geometry, we would need a second set of modes that live inside. And so this is associated with that, it's roughly centered on that geodesic, and I'll call those B tilde. So B is an outgoing Hawking mode. B tilde is called a Hawking partner. Now, if you want to study sort of the physics of an infalling observer, my horizon was not supposed to get tangent with that light ray. Anyway, if you want to study the physics of an infalling observer, it wouldn't be convenient to use these modes which have this discontinuity in them, half covering this side and half covering this side. It would be natural to describe the physics in terms of a set of modes that were smooth across the horizon. And we'll call those A. Now at Stanford, this is called B, this is called A, and this doesn't have a name, just to provide a translation. But okay, now, and of course, so there's two complete sets of modes, the BB tildes and the A's. And there, because of the horizon, there's a very nonlinear relation between the time seen by the infalling observer and the time at which these rays are seen by the outside observer. In particular, in the finite period of time it takes the infalling observer to reach the horizon, those light rays have spanned an infinite time as seen by the outgoing observer. It's a very nonlinear relation, and so in particular that means that positive frequency for these is mixed with positive and negative frequencies for these modes. And again, A and B are just numbers, and again, these should all be matrices in some complete set, but I'm being schematic. Good. So that's the first important thing, just that these two sets of modes are relevant and that they are Bogoliubov transformed with respect to each other. Now, if you think about this wave packet B, as you look at it earlier and earlier, you can, the reason I like these coordinates as opposed, say, to Penrose conformal coordinates is that they emphasize the fact that as you go back in as you follow these packets back in time, they're becoming more and more blue shifted. They're higher and higher frequency as they would be encountered by earlier and earlier infalling observers. And therefore, the adiabatic principle tells you that these modes have to be essentially empty. Whatever state the black hole is in, we assume this is informed by collapse in some fairly generic way. Whatever state the black hole is in, just by the adiabatic principle, if we haven't done anything too dramatic, these high energy modes will be empty, and therefore, because of the Bogoliubov transformation, they are not in the vacuum as seen by the observer at infinity, and this is Hawking radiation. And this is, if you think about it, this is, I think, uses the fewest assumptions in deriving Hawking radiation. In particular, there's no issue of Transplanckian physics. Really, the physics is driven by the use of the adiabatic principle at this point. If we went into more detail, we'd find more explicitly that the state is, with some normalization, well, again, a Bogoliubov transform state. It's obtained on the B and B tilde vacuum. Again, the tilde is the inside mode, the B is the outgoing mode. It's obtained from the vacuum for those modes. For the other set of modes, as a squeezed state, Bogoliubov transform state, and in particular, this means that the modes B moving out and B tilde moving in are entangled. So the two takeaways from this part of the talk are just a simple and robust derivation of Hawking radiation and the entanglement between the outgoing Hawking photon and something left behind in the black hole. Okay, so now to see why this is a problem, I want to draw a graph that was first, I think, drawn by Don Page, and it's really useful for having in mind. So what I'm plotting vertically is various entropies, and I'll tell you what the entropies are. And what I'm plotting horizontally, so this is going to be the life, is basically time. So I'm going to be considering a black hole that forms at time 0, again, and collapses in some way, and then evaporates over time, and at this time here, it disappears, it finishes evaporating. And again, it could be time, or it could be the number of Hawking photons, or just some measure of how long the evaporation process is going on. And there are 3 entropies I'm going to be talking about. The first is the following. So as the black hole starts, and then it starts evaporating, emitting photons. And so the first is the entanglement entropy between the Hawking radiation and the black hole. Hawking radiation and the black hole. The second, which I'll call S sub Hawking radiation, is the fine-grained entropy, the von Neumann entropy of the Hawking radiation. And the total Hawking radiation at any given time, so the von Neumann entropy of the Hawking radiation. And again, this is trace rho log rho for the exact density matrix, and it's simply equal to this. Because the fact that the radiation is entangled with the black hole means the radiation by itself is not in the pure state, and vice versa. So these two things are the same thing. And there's a third thing which is the same thing, which is the entropy of the black hole at a given time. Again, by S black hole, I mean, again, the von Neumann, the fine-grained entropy, the entropy you get out of the exact quantum density matrix for the system, the von Neumann entropy of the black hole. And the scales of these entropies are enormous. So for all practical purposes, we can suppose, for this purpose, that the black hole starts in a pure state, the whole system is in a pure state, and that in turn means that these three are all equal, that its fundamental which comes from its entanglement with the outgoing radiation. So these are all equal. And you see that that at each step, so this is happening sort of once per light crossing time of the life of the black hole. At each step, this process is happening, and it's increasing the entanglement between the radiation and the hole by an amount of order 1. And so this curve just slopes upwards. S sub E equals S sub Hawking radiation equals S sub black hole. Slopes upwards. Now, once the black hole gets to Planck side, which is really the very end here, well, the last details of the curve we don't know, but then the black hole finishes evaporating, it disappears, nothing more happens, except that, of course, once the black hole has disappeared, two of these things don't mean anything anymore because the black hole is not there, so it doesn't have, so these things are just simply no longer meaningful in the system. All that's left is the Hawking radiation, and it has, again, it's in this very mixed state. It's described by a density matrix with a very large entropy, and so seemingly one has described evolution of pure states into mixed states. And this was Hawking's original argument. This is Hawking's original argument, and in 40 years of trying to poke holes in it and trying to find subtleties, it seems that it's entirely correct within the framework of quantum gravity as an effective field theory. For example, you can start asking about higher, isn't this a very subtle, aren't there very subtle correlations here? What if we think about higher order effects where, different Hawking partners exchange gravitons? And that would have an order, that might change the slope of this line by an amount of order epsilon, but it doesn't change the basic fact that what's being emitted has entanglement with what's left behind. And moreover, if you consider the earlier photons emitted, the things that they're entangled with are behind the horizon where they can no longer interact with the outgoing radiation. So there's no way to extract in local physics the entanglement that's already built up. And so this is what happens. Okay, so it seems pretty convincing. We could just stop here and say that's the answer. Now,
sorry.
Question? Yeah.
But you assume that, that when black hole gets smaller and smaller, its size gets closer to singularity.
Yes.
You no longer can think of that the regime is sort of quasi-classical, so it's a very quantum regime of the gravity.
Yes.
And so at the very small times that this argument may not work.
Right here. So let's come back. Good. Let's come back to that in a little bit. I'll talk about that time in a little bit. But actually, there's another curve which is worth drawing here, which is the Bekenstein-Hawking entropy of the black hole. So the black hole starts out big and gets small. It starts out big and then gets small. And again, by the time it evaporates, it has zero size. And it's going to zero, or maybe a very small number that we'll come back to. So this is S Beck-Hawk, which behaves like a thermodynamic entropy. So the thing I called S sub BH is the fine-grained entropy of the system. The thing S Beck-Hawk is the thermodynamic coarse-grained entropy. And it's not surprising to find a system in which this is smaller than this, but it's very surprising, it doesn't happen in ordinary statistical mechanics, to find a system whose fine-grained entropy is greater than its coarse-grained entropy. And so this is why, we'll come back, again, what happens at the last instance of the operation are interesting, and we'll come back to it. But this is why this is a problem. This is a problem long before the Planck regime sets in. Here the black hole is of order half its original size, and the curvature is small, and yet there's a deviation between what quantum field theory in curved space is saying, which should be robust, and what we expect from statistical mechanics. In fact, if this were not a black hole but a lump of coal, what would happen is the following. So here's a lump of coal. So we heat it up, it starts to burn, it emits photons. And indeed, the first few photons that are emitted are entangled with the remaining coal, and it will start to follow a curve like this. But inside they're correlated with phonons and things which are rattling around, and after a while, these phonons will rattle to the surface and excite a photon and be emitted. And so initially these photons are entangled with these, but eventually the photons are entangled with photons that are emitted later. And so what happens is the entropy rises for a while, and if this is a very efficient thermalizer, it might actually go on for a very long time following this curve, but eventually it will follow a curve like that. And because coal is described by ordinary quantum mechanics where pure states evolve to pure states, the von Neumann entropy of the emitted radiation goes to zero just exactly when the coal is finished burning. And Page argued, Don Page is again the first one who drew these various curves, and who argued in particular that if the black hole Hawking radiation system is exploring a typical state at any given time, again, as you would expect for a chaotic system, you actually follow these two curves extremely closely. But that's not important for any really important thing I'll say, but it's still useful to visualize that you kind of follow the fine-grained curve for the first half and the coarse-grained curve for the second. So if a black hole behaves like a lump of coal, this is what has to happen. The problem is that, of course, coal doesn't have a horizon. These phonons, which are the analog of the inner Hawking modes, can rattle around for a while and get out, whereas the black hole has an event horizon. And here, the geometry is still semi-classical enough to say that the event horizon is intact. And so, with local physics, if quantum gravity as an effective field theory is valid, we can't do this. We have to do this. Okay. Now, okay. So I want to mention one more possibility. Okay, actually, two more things. Oh, no, I want to mention one more thing now, and then I'll be finished with my first item. So it is worth thinking about what happens at the very end stages of the evaporation here when the black hole is Planck size, and we don't know the physics. And one logical possibility is that at some point the evaporation stops. The black hole doesn't disappear completely. It remains as some small object, Planck-sized object. And so I really do have three curves at all times. But we'll call this little thing that's left behind not a black hole, but a remnant. And again, this is equal to the entanglement of the Hawking radiation and the remnant. So in this case, ordinary quantum mechanics would be preserved because, again, you'd have a pure state of the system. But it's unappealing for many reasons, the most striking of which is simply that it somehow is inconsistent with the interpretation of the Bekenstein-Hawking radiation as a thermodynamic entropy, because that requires that's already got a problem with that here. So in this subject, if you look at sort of the first 20 years after Hawking's 1976 paper, there were three basic possibilities. Information is lost in the way he described. Information gets out in the Hawking radiation via some process that somehow can effectively transmit information faster than light, get it from behind the horizon to the exterior, or remnants. And there are subcategories of each of these. But if you look at the large number of papers that were written, pretty much every one can be grouped into one of the three. Each of these threes has unattractive features. But for about 20 years, you could argue and argue and vote, but not know really what the answer was.
But Joe,
yes,
there was also a scenario enunciated that looks a lot like, at the coarse grain level, what's now called the firewall scenario, where you end up with a new kind of object with a surface or interface just outside the horizon or replacing the horizon. And you have some new physics there.
So where is that in this curve? That's not up here, but sort of down here?
Yeah.
So good. So
well,
right.
So
an
intermediate point where it's not planking.
Right. So somehow, good. So somehow before the geometry, so it's a scenario that somehow before the geometry becomes Planckian, right?
There's information transfer outside, and in that case, it's violent, like the firewall story. Yeah. It uses some remnant-like object, massive remnant-like object.
So I finished my item one. So I should pause for questions before I steam ahead. No, I think you're right. I think that does not. That does not. The scenario you've enunciated doesn't fall in one of these three. So I shouldn't say.
So that's the fourth alternative.
Right.
Put out.
Right. Any further questions about what I've said?
Sorry. Also, can I find out if those coordinates that you use?
Yes.
This result of Hawking, does it depend much on the fact that it covers only some pieces?
Yeah, it depends vitally on the fact that there is a horizon. That's right. It is. This happens precisely because the geometry has a horizon. Happens because light rays that reach infinity don't cover the whole space. Yeah.
So you can come to similar conclusion in empty space by accelerating.
Right. That's right. That's the Riddler story. That's right. That's an eternally accelerated observer in flat space. We'll see also thermal radiation is It's the limit of the same calculation. Okay. So actually, just to come back to I would actually say the firewall is still in this class. Although that doesn't mean, but again, not all ideas are in this class.
There's something you smack into near the
Yeah, but the information still comes out with the Hawking radiation. So now we think we know the answer. We think we know which it is of these three, of course, because we have ADS-CFT duality. And so we can consider this entire discussion taking place in an anti-de Sitter box. Black hole forms and evaporates in energy spot. And there, of course, we know there's a dual description in terms of a gauge theory. And so pure states don't evolve to mixed states. Also, it requires a bit more detailed information, understanding of the dual gauge theory, but we know that ordinary gauge theories don't have an arbitrarily large number of states at very low energy, and so it's also not compatible with, oops, I erased the wrong one, sorry. You tricked me. Okay, there, okay. And so information is not lost, it's not remnants, the information comes out, and seemingly with the Hawking radiation. Interesting, because this is the sort of the most, well, in some ways it's the most conservative. It says we draw the same curve for a black hole and for a lump of burning coal. But it also means that somehow gravity as an effective field theory breaks down in a regime where we have every reason to think that it applies. Now, and so it would be nice to understand exactly how this happens. What is the bulk physics that makes this possible? So before actually ADS-CFT, there was a scenario due to Tufte, Preskel, but especially Susskind, called black hole complementarity. This is just a scenario. And so again, so the idea of black hole complementarity is that quantum gravity's effective field theory is not close to the right answer. It emerges as an approximation, but the locality. So when we think of effective field theories, we normally think of effective field theories as being derived from higher energy but still local theories. The idea here is that the underlying theory, whatever it is really not local at all, and locality is emergent. And the idea that goes with that then, so we can one way to think about before I explain, one way to think about the paradox is the following. Let's think about our Hawking photon B again, and the local dynamics that we discussed means that it has to be entangled with B tilde. But if the entire ensemble of Hawking photons is in a pure state, B has to be entangled with the rest of the Hawking photons. And that mutual entanglement is inconsistent. Strong subadditivity of the entropy says that if we consider first the system consisting of just the Hawking photon and its partner, and the von Neumann entropy of that density matrix, then the system consisting of the outgoing Hawking photon and all the rest of the Hawking photons, that the I'm going to put this in a direction that gives me a problem. That's the direction. Yes. Okay. It says that the von Neumann entropys for the various subsystems behave in this way, and now this is zero. This is zero because the two Hawking modes are in a pure state. This is zero because by assumption the total system's in a pure, the information is not lost. The total system is in a pure state. The left-hand side is zero, but the right-hand side is certainly not zero because the density matrix for B is thermal. So another way to state this problem is that that violates strong subadditivity. And now the idea of black hole complementarity is that really things are not nearly as local as we want to think, and that in particular, and so the different observers see information in different places. An observer who jumps into the black hole and interacts with both the Hawking modes near the horizon sees this entanglement. This observer, the infalling observer, sees SB tilde equals 0. The observer who stays outside the horizon, however, just sees pure Hawking radiation. They see SB Hawking radiation minus B equals 0. And so, okay, so they each see what they need to see, this to get quantum field theory to behave right near the horizon, this to preserve purity of states, and they can't compare notes. This is the logic of the idea is that they can't compare notes, and so one shouldn't so one shouldn't think of a single state that describes all of these things: the outgoing mode, the ingoing mode, and the rest of the Hawking radiation, because no single observer can see them all. And so it's like a new relativity principle. It's just a scenario, but it's interesting because, again, this came along in 1993, and if you think about ADS-CFT, it's kind of a realization of that, because in ADS-CFT, you have the boundary description where everything is on the boundary. You have the bulk description where everything is in the bulk, and so in flavor, it's very much like this, where there's a very strong fundamental violation of your ability to localize a quantum state. So this was supposed to preserve quantum mechanics in the way the ADS-CFT does, but at the cost of locality being violated in a subtle but long-ranged way.
So somehow in the proof of the strong subactivity, the observers have to come in somewhere, right?
No, it's just a statement about density matrices.
But aren't you saying that, yeah, so that's what I thought, but you're saying that the observer, there's no single observer that could see both terms on the left-hand side.
That's right.
A given observer can only see one term.
That was that. So
where did that come in?
So this doesn't come into strong subactivity. This comes in. So the assertion is that when you formulate quantum gravity, you should not use Hilbert space. So this is Lenny's assertion. Mm-hmm. You should not use Hilbert spaces that are any larger than a single observer can see. Mm-hmm. And so with any relation like this from quantum mechanics, you don't apply it in a Hilbert space larger than a single observer can see. Okay. Now, and various thought experiments seem to say this makes sense, and it seemed, like I said, it seemed to me very appealing because it again dovetails with the way ADS-CFT works. But in fact, it doesn't seem to work, and it works maybe for Hawking photons that are emitted in this early phase, but it doesn't work seemingly for Hawking photons that are emitted in this later phase. And I have to say that, okay, it was again Page who first drew this curve, but actually this subject has been very much influenced by ideas from quantum information, and especially Hayden and Preskill, who pointed out that the way basically you can extract information from a black hole changes radically depending on whether you're on this part of its life or this part of its life. And what I'll be doing is much more simple-minded than what they did. So I want to suppose that we're considering one of the late Hawking photons, B. And now I want to consider not all the Hawking radiation, but just the earlier Hawking radiation, half and a bit more.
Didn't they say mirror behavior began at something like the fast scrambling time?
No. Mirror behavior begins at the Page time.
No, Hayden and Preskill.
No. You need to have captured. No, it's half the Hawking photons. Yeah. Now the strong so the first point so if I decorate my picture here, we have the earlier Hawking radiation.
Sorry, could you ask about that again? Can you argue that the potential corrections within the framework of effective field theory of SB with HR minus B would still be small compared to SB?
Okay, so good. So this is a number of order 1. These are So you've already got a problem because if these are 0. Now I've oversimplified a little bit because of gray body effects. Because in fact the outgoing photons roughly half the time reflect back in. It's not as stark as it seems. It's like 0 and a half. So there are effects which seemingly mollify this, but you can't get down to where you always end up comparing 0 to a positive quantity in the wrong direction. Yeah. So if I decorate my earlier picture with the early radiation, so now a single observer falling in can interact with all of these things, E, B, and B tilde. And so we need to consider a Hilbert space that contains all of them. But now that's enough to have a problem because once you've captured somewhat more than half the Hawking photons, basically everything that comes out later has to be entangled with something in what you've already captured. And because the sizes of the Hilbert spaces are exponential in the number of Hawking photons, this Hilbert space is much larger than what's left. And again, this is their observation. And so this mode has to be entangled with one of these. And so now we have, again, our problem that there are 3 things, all of which are seemingly visible to one observer, and yet there isn't it's not consistent with quantum mechanics. Now, I'm saying a number of things. First off, this inequality was first applied to black holes by Samir Mathur, and Samir Mathur has done a tremendous amount to make the black hole information paradox sharper. He's also argued that something funny happens at the horizon, which may ultimately be the same thing, although there are many questions. But in any case, Mathur has done a lot to make all of this sharper. Also, this argument may seem rather abstract, but I'll tell you that it began really with an attempt to build models of black hole complementarity, not to prove you couldn't do it, but to make models of how this would work, just toy models with series of bits. And again, Mathur and Steve Giddings in particular over the years have tried to make models of how the black hole would release information. And it was the failure to make a model that was consistent with this idea of complementarity that ultimately led to this no-go theorem. So,
but you said the free-falling
yes,
observer would see the Hawking radiation?
The infrared observer can measure these modes. Yes, there's quantum fields, right? And they can see this one as the earlier Hawking radiation as well. Yeah.
No. If you describe his Hilbert space, he may not see those modes.
Which ones?
He'd be more like A.
Wait.
Seeing
So,
the A mode.
no, he can measure whatever he can have an apparatus which is tuned to measure any of these modes. I mean, there's no reason in principle. He can build.
If B were occupied in a non-Hawking-like fashion, that would be seen as a high-energy particle by the infall mechanism. So
something like n sub b is the number operator for b. B dagger b is a permission operator. They can measure it, even though it's subtle to measure. It's not. But there's not. objection in principle. Now, so if you think about what goes in here, so again, it's been assumed that the Hawking radiation is pure, information is not lost. It's been assumed that the physics is given by effective field theory near the horizon. And actually, there's an implicit assumption. There's more than one, but one of them, not implicit, it was explicit, is that nothing happens to this mode B as it travels from the near horizon region out to infinity, so that, okay, now if it interacted in some unexpected way, we need in some way the entanglement between these two modes to be transferred to these modes. And if so, and in effective field theory, it just propagates freely. That doesn't happen. So there are three assumptions, basically: effective field theory across the horizon, purity, non-loss of information, and effective field theory sort of outside the horizon. And certainly when we stumbled on this, I thought that this was the weak link. We know that ADS-CFT makes physics non-local. And so it didn't seem problematic to me that non-locality would extend, past the horizon in some tangible way. But very quickly, and Don, I think, beat this into me, it was clear that it was very, very hard, if not impossible, to make a model of this. First of all, the effect has to be large, not subtle. But secondly, if you think you have a mechanism that does it, there are always ways that you can make thought experiments that defeat it. And so, again, we all trust ADS-CFT. Nobody's going to argue that information is lost. Steve Giddings, in particular, is still especially pursuing this option through models that actually physically transport quanta in space-like directions. But we came down saying that the loss of this entanglement seemed like probably the most conservative thing. What does that mean? Well, what it means is if these two bits are not entangled, then this mode is not in its vacuum. And this is true mode by mode, and that's the firewall. So that's the base. I was supposed to sort of give you an update, but this is bringing you up to 2 years ago now. This is the original firewall argument. Unless there's questions, I'll now give you a version of it, which is, I think, a little bit more. Well, you can see what you think of it. It's a little bit, more ADS-CFT-ish. That's a good thing. Here's our black hole, and we're now going to put it in ADS space. So there's the boundary. There's where the CFT lives, and the mode B here, it propagates out to the boundary, and using the standard dictionary, we can find for the mode B in the bulk a dual operator in the CFT. Okay. And then we can consider a basis for the CFT in which the number operator is diagonal. So it's B dagger B diagonal. So this takes it. So this number operator takes a definite value, 1, 2, 3, or 4, so on. And now in this, let's think about that, because in the A vacuum, in the state which did not have excitations at the horizon, so A is in its vacuum state. The mode B we saw was not in its vacuum state. Moreover, it's in this Bogoliubov transform state. It's in a state that has a thermal distribution of possible B excitations. And by the way, the use of this basis, I think, especially emphasized by Busso. So if we consider a basis in which that's diagonal, what we know is that none of these states are vacuum near the horizon, because none of them have the thermal distribution for this number operator that the vacuum state has. So all such states have this number operator. I'm sorry, all such states have the number operator for the infaller's mode. So the infaller receives positive. Again, if this were zero, again, this is an argument. The argument again is if this were 0, then the B state would be this thermal state, and this would not be diagonal. So if this is diagonal, this is not 0, and it's a number operator, so it's positive.
So Joe, could you back up a second?
Yes.
So you said that B and B, that twiddle are not entangled. Is that a hypothesis or a statement? Or?
I'm saying no. I'm sorry. You've backed me up to where I'm trying to keep these and giving up this.
Okay. So you want to say SBB twiddle is not 0.
If this is not 0,
then BB dagger, BB twiddle are not entangled.
And then
it's not in its vacuum.
Not in its vacuum state. That's the original firewall argument.
What is this equation?
This is a new argument. Okay, this is a new argument. Hat here means it lives in the dual conformal field theory.
That's hat,
hat.
Not twiddle.
That's a hat. Sorry, I should have made it hat here.
Oh, okay, that was mine.
There. Okay, so this is using now ADS-CFT and the fact that operators outside the black hole have duals in the CFT, and then again, so we can choose a basis in which is a diagonal. All such basis states have excitations, and again, we can do this for any number of modes. So every mode in this basis has an order 1 probability to be excited. Now, but of course, we can turn this into a basis by considering now the trace over the states in some energy, basically a microcanonical trace. And since this is positive in every state of the basis, it is positive in the microcanonical ensemble. And so this says that typical states so this is now basis independent, and it says that typical states in the typical thermal states in the CFT, which look like black holes, if you look at what's inside them, they have order 1 probability for each mode to be excited. So this ultimately uses very similar assumptions to the earlier argument, but it uses a little bit less of the observers and more just calculation. And so it perhaps is more robust. Okay, so this is the end of part 2. These are the arguments why seemingly black holes must have, in this region where the adiabatic principle would say just a vacuum, they have a shell or wall of particles whose at least, if nothing else happens first, they have a shell or wall of particles which presumably back reacts so strongly that the interior is gone entirely.
You think an observer on the ADS boundary can see what the free-falling observers?
No, good question. I will come back to that. The observer on the boundary, but since you asked, it's worth emphasizing the structure of the argument because it's suspicious. That is, we use the fact that the observer on the boundary can see this thing, and we use the fact that local field theory near the horizon, if it's valid, if the horizon satisfies local field theory, knowing this thing tells you something about this thing. He doesn't see this directly, and I'll come back to that at the very end.
Yeah, well, that's what I meant when I said that the free-falling observer would define a different Hilbert space, I think, and would not see these B modes.
Well, so I mean, the infalling observer can certainly can.
It's the analog of going from the Rindler observer back to Minkowski space.
The Rindler observer could build a device that would measure the Minkowski modes.
That's right. That's right.
I mean, so when I say
but then he couldn't go back to Minkowski space.
Well, no, I'm just saying as the well, yeah.
Yeah.
I
mean, I did that. myself, calculation, so that you can see that if you actually do measure, if the Rindler observer actually measures Minkowski modes, then you're in an excited state from a Minkowski point of view. You can't go back to the vacuum Minkowski space. If you go back to
Right.
it's frame dependent is what I'm saying. The Hilbert space is frame dependent.
Well,
this
this observer should have a Hilbert space which basically assigns an amplitude to any given. Well, it should be a wave. This observer should their physics is described by a wave function, which is the wave function for the electromagnetic field in this region. And any property of any they should be able to make. That wave function, first of all, should make sense if quantum mechanics makes sense, but we can show that the point of this argument is that no such wave function makes sense, because if they had chosen to measure, there is no wave function you can write down that both accounts for any measurement they might choose to make here plus the measurement they made on the earlier radiation.
That I'm not sure about. What I do know is that the Minkowski observer, if the Rindler observer measures the Hawking radiation, the Minkowski observer would see radiation being emitted by the measurement apparatus.
That's okay. I don't think any of that, I don't think any of that changes the fact that there's no consistent wave function. There's no wave function for the electromagnetic field in their vicinity, which is consistent with everything it should be consistent with. That's sort of the nature of the argument. And again, this one, well, this argument should be equivalent, but it uses fewer observers. Now, so I have just a little time, but I don't have that much about the responses. And I'm going to mention just two of the many. So the first one is this paper by Papadimos and Raju. And I'll explain how they evade this version here. And it's because their operators B and B dagger are themselves functions of the state. So in normal quantum mechanics, you have operators and you take their expectative as in states, but the operators themselves don't depend on the state. The operators are state dependent. And actually this idea that operators need to be, well, the Verlindas and the Mora. Now that may not sound so bad because these operators are nonlinear in a very tricky way, such that every single basis state of this type has a firewall, but a typical state, a typical superposition of states, does not. And again, you can't do that with a linear operator, but if your operator is nonlinear, it can do what I just said.
No? What do you mean? I think you meant the A depends on the state?
Well, everything. Sorry, you're right, A. The things inside. Thank you. The A depends. Sorry, it's not B. I'm sorry. It's at this point. It's A that depends on the state. Thank you. It's right. So there is kind of a standard construction of the outside bulk operators, which is just ordinary linear. They are background dependent, but they're linear operators. But the construction behind the horizon, again, requires the operator. If you want to construct, if you want somehow to avoid having a firewall, the operators have to be state dependent. Now,
so is this outside the framework of the usual quantum mechanics?
It is outside the framework of the usual quantum mechanics.
I disagree with that.
Okay.
Sorry, was that Mark's disagreeing?
Yeah.
Okay, why do you disagree, Mark?
Well, because we make state-dependent measurements all the time. If I want to measure that podium there, I need to be in a state where the podium exists. That's not a violation of quantum mechanics for me to measure properties of the podium.
So when we define, so in quantum gravity, one tries to define relational observables, things that are, again, you only measure the podium if it's there, for instance.
Yeah.
But those are always given by linear operators. They're field dependent. They're field, that is, they depend, the operators have a complicated nonlinear dependence on the metric and the other fields. But they are still linear operators.
No, because I can write down many states of the universe where there is no podium.
That's right, that's right,
And
that's
then,
right.
Then my measurement will be meaningless. It's not at all clear to me that the Papadopoulos and Raju state dependence is not state dependence of that type, where you need to know properties of the state before you can even say what the measurement is.
See, what you've described can all be incorporated in terms of multiplying my operator by a projection operator onto the podium or whatever it was being there. Okay. Theirs cannot be. That's all within this linear context. Theirs cannot be written in terms of simple projection operators. The formula for I believe you have never written down a formula like this, where the formula for the operators themselves depends on the wave functions. Now, this may be a feature, not a bug. I have to say, I have some sympathy for this. Don, wherever he is, has none whatsoever.
Does this mean giving up linear superposition?
It means giving up to some extent, in a way that might be subtle. And the problem is, this paper doesn't sort of, but it deliberately doesn't sort of try to discuss all possible experiments one might do. And Don's objection, which is a good one, is that if you start asking questions that would probe superposition, in effect, they don't have a prescription. I still say I actually have some sympathy for it and think that maybe it's fixable, but again, this is in terms of where the field is. At the last meeting we had, which was I guess just 2 months ago at Princeton, this was kind of the main subject of discussion, and these questions about does this make sense were central. But anyway, this right now is a framework. It's not a theory. It's a scenario, it's a scenario for a framework.
No, but can you explain maybe briefly how does this solve this second version of the paradox?
So there's a rather odd thing that can happen in systems of many states, which is the following. Suppose the firewall argument is wrong. That means typical random states in the Hilbert space are in the A vacuum. Okay? Yet we know that if we have sort of field theory, there's lots of states which are not the A vacuum, which react by exciting it. So how do we how do we reconcile the idea that typical states are in the vacuum with the fact that there are lots of states which are not the vacuum? And what their formula does is, for any state, it requires that for any state that you give it, that you give them, they can identify uniquely the typical state from which it was raised. And within a limited framework of what you do to the state, you can do that. The problem is, again, there's a limited set of questions. But it's rather interesting. If I give you a state of a quantum chaotic system in which I've acted with some local operator, you can deduce what the state was. You know, even though the original state was typical, and this is you can deduce what I did to it. You can deduce what state I got it from. And the essence of their construction is that given a state, given any state, you figure out what is the associated typical state, and then you kind of build a Hilbert space with the assumption that that typical state was the vacuum.
But since the question was raised, if I understand correctly, if you give Papadopoulos and Raju this microcanonical ensemble and ask what is the expectation value of their operator in it, as far as I can tell, they really have no prescription for calculating that. What they say is that this is not the right question to ask because in our framework we have a different notion of what we mean by typical, which is not defined by taking density matrices as ensembles and computing expectation values.
Well, I mean, they would say you could calculate. Oh, you mean sorry. Well, but so they. I mean, I think in their paper they don't talk about they don't talk about this basis.
And
right,
they don't talk about computing things in these impure states as well. In these sort of ensemble states, if I understand correctly. They have a different notion of...
Yeah, okay, right.
They have made the conclusion because they claimed in their framework the notion of typicality is different. Yeah. It is not defined by doing some computation with this ensemble, and in fact, they, if I understand correctly, don't know how to do a computation in this ensemble exactly because their operators are dependent on a choice of pure state, and what do you do in this completely mixed state? So they have a different mathematical framework that they're beginning to fill out that would...
Yeah. I mean, another thing that's perhaps the same is that in linear quantum mechanics, we know that we can sort of include the observer in the system or treat them as outside to get the same answer. That's why Copenhagen works.
Right.
In nonlinear quantum mechanics, they give you different answers. And what Don is saying is you have to make a choice before you compute. So it's suspicious. And if you're gonna go and change the rules of quantum mechanics in this way, I'm again sympathetic to it, but there's a lot of questions that need to be answered. So now finally, ER equals ETR. So change of subject, at least initially. It really is a change of subject for the most part. So if you take the vacuum, so instead of considering black holes that sort of form and collapse, as I was imagining before, if you just take the maximum vacuum solution of Einstein's equation with a negative cosmological constant, you get the two-sided ADS black hole. You could also consider a two-sided Minkowski black hole. But for the two-sided ADS black hole, if you can now consider correlators via the ADS CFT duality, you can consider correlative operators, and you have two boundaries you can put them on. And the claim is that if you consider this bulk question, that is ADS space perturbed in by the usual dictionary at the boundary, and you need a prescription for at least the initial singularity, which is the Hartle-Hawking state, then it follows from the usual ADS CFT duality that this geometry calculates field theory correlators. And it's a field theory which is a tensor product of a left field theory and a right field theory, in which the state is this thermal field state. Is normalized appropriately. And then some overall energy eigenstates, e to the minus beta e sub n over 2, and then diagonal in energy between right and left. So it's a double, there's a right Hilbert space, left Hilbert space. This state is diagonal in the energy basis with this normalization. If you have operators just on one side, this expression just builds for you the usual thermal density matrix, but you have them on both sides, then it's fancier. And again, you can think of this geometry as a continuation of just the Euclidean ADS geometry, ADS black hole, where you cut through the middle and then Lorentz would rotate. And so it seems to be true that this geometry calculates this correlator. Now this geometry has no firewall. It's a nice smooth geometry, but again, the firewall, if it exists, doesn't exist in all states. It exists only in typical states, and so this is clearly a very atypical state. In fact, one of the things that was quickly done, Stanford and Schenker considered the effect of perturbations of this geometry, and Don and I considered what happens if you replace the thermal field state with a really random state in the two-sided geometry, and you get a very different story. It's not clear whether there's a firewall or not. What's clear is that for more typical states of the system, if there's a throat, it's very long. There's lots of matter in between that supports this geometry. So the correlators between the two sides are very much smaller. But unfortunately, these methods don't answer what happens. let me just get to the ER equals EPR idea. So what I've told you here, we can kind of summarize as saying ER implies EPR. Namely, so Einstein-Rosen refers to this geometry, the Einstein-Rosen bridge. If we have this geometry, the claim is that the boundary theories are entangled in this way, and so EPR is shorthand here for entanglement. So this connected geometry gives rise to entanglement. And the stronger conjecture is that it also goes in the reverse direction. So this is the last thing I'll talk about. Let's go back to our earlier black hole. This is Maldacena and Susskind's thought experiment. Let's go back to our earlier black hole, which now has formed and is evaporated down past the page time, or to the page time, it's emitted half its Hawking photons. We now collect those early Hawking photons and we carry them over here. And we no longer interact with the original black hole at all. We take those Hawking photons, we collapse them into a second black hole, and we do appropriate quantum computations on the state such that the two black hole system is this entangled state. And now the question is, this was a black hole that formed and collapsed. It's supposed to not have two, whether or not it has a firewall, it has, it's supposed to only have one side. But now, if we've put it in this state here, have we somehow, by these manipulations that we did way far over here, created, not on the board you can see it, but inside a geometric connection between these two black holes? And so now there's two possibilities. The first possibility, so that's a strange thing. The first possibility is no. That is that having this particular entangled state doesn't necessarily give rise to this geometry. That is, knowing what the state of the CFTs is does not uniquely specify the interior. And in fact, this is something that Don and Aaron Wall were exploring and arguing even before the firewall came along, that in fact there is an intrinsic ambiguity in ADS-CFT, and so there's additional data which is needed to tell you what the bulk is doing beyond what the boundary CFTs are doing. They call this, for better or worse, super selection sectors. Okay, so that's one possibility, which is disturbing if true, because it means that there's something missing in our theory of quantum gravity. The other possibility is the answer is yes, that if you by this elaborate procedure, you put the system in this particular state, then in fact it's one-to-one. If you have this state, you have this geometry. And that's rather odd, because if we have this state, we can perturb it. We can add a quantum here, and such a way that someone who jumps, so this was our original black hole, and this one is the one that we've created in the other room. You could act on this one in such a way to send in a quantum which the observer who jumps in from the other side in the original black hole could see. You could send them a message. And now this is very strange, because if we think about the EPR experiment, within ordinary quantum mechanics, if I have two systems that are entangled but not interacting, there is nothing that I can do to system 2, nothing local that I can do to system 2 that would in any way send a message or be detectable in system 1. That is that's basic to quantum mechanics. And yet somehow, if we simply take this simple mathematical relation and assume again that it's an equality, that it goes both ways, you're led to the conclusion that you can effectively, by operations on the entangled system, send information, but not to someone, to a general observer. It has to be to an observer who is falling behind the horizon of this black hole. So again, maybe there is some larger sense in which this lives within linear quantum mechanics, but it certainly sounds, again, like it has gone outside the normal linear quantum mechanics. Now, maybe again that's a feature, not a bug. But what this lacks, like the Papadimos-Raju proposal, is really a complete, consistent set of rules. For example, suppose you process the black hole, put it in a state, then you act to send in this message. Then you whack it a bit, then you run your quantum computer and you put it back in this state and you send a different message. What message is received by the infalling observer? And it doesn't seem to me that there's any consistent set of rules that you can make in this context. And so there's this. Maybe there is no such rule. If there's no such rule, this is not an equality, and it means that ADS-CFT, even in this two-sided case, has to be supplemented by additional data to say what the interior is doing. But I have to say, I told you that in the first 20 years of Hawking's paradox, we kind of ran around in circles, were very confused, and then we had a fact, ADS-CFT duality, which told us where the information goes. And also, it seemed to be a complete theory of quantum gravity in ADS space. It knows about, if you could, so even without solving it, it tells you that ordinary quantum mechanics holds. If you could solve the theory, you would know the exact energy spectrum of the black hole. You would know how it responds to any kind of perturbation you make, even in its, how does the quantum wave function, basically the black hole S matrix, all of that would be in gauge theory. That seems to be everything. But now ADS-CFT seems to be rather helpless in the face of this paradox. So the question is, suppose you could even solve the gauge theory. Suppose you had the power to solve the gauge theory. What question would you ask it to tell you what's happening inside the black hole? And we have a dictionary at the boundary. We can kind of push it in differentially. But once you get past the horizon, you really can't push it in any further. And it just seems as though that ADS-CFT is lacking this information. As Marty pointed out, the ADS, when I used ADS-CFT in that second firewall argument, I used it to talk about the B modes outside, and then used effective field theory to deduce things about the A modes that cross the boundary. I didn't try to represent the A modes within the CFT because we don't know how, and probably they aren't there at all. So the bottom line is that our theory of quantum gravity is not as complete as we thought. I think what we're missing is an independent, non-perturbative formulation of the bulk. We've been sort of living with the non-perturbative formulation of the CFT, but we don't have an independent. And there you have it. That's your job.
Joe?
Yeah.
I guess two questions.
Yeah.
So in this construction, if you form a black hole by ordinary collapse, wait for it to evaporate, collect all the Hawking quanta, take it over to another room, and form another black hole.
Yeah.
Then the black holes exist at very different times, right? So it's not really like having two black holes with a wormhole, right?
Well, if I have two so one of the interesting things that maybe it was known before, but they emphasized it, Polchinski and Tuscan. So you can form when you form pairs of black holes by tunneling, they form naturally in this state at the same time.
Oh, if you pair create black holes, then they are
right. But now you can put one. Now you can do a twin paradox, right? You can put one in the rocket ship and carry it around. Their times are once they're created, their times are no longer in sync.
There's no problem, if you're talking about pair creating charged black holes and electric or magnetic field. I mean, I'm fine with that. This particular construction, forming one from collapse, collecting the Hawking radiation, then going over collapsing that's
But even when I'm saying even when you form them in the way you like, there's no relation between their time coordinates. You can keep one at rest and boost the other one around, so their time coordinates are totally out of sync.
Sure.
So I'm not sure there's anything different about this case than that.
One black hole evaporates. You think of the space as being described, by just radiation. If you then form another black hole out of that radiation, I don't think you get to these.
Do you just use half of it, or do you wait for all of it? I think you just use half the radiation.
Right.
Use only half.
Sorry, I'm using half the radiation. I'm keeping half.
Oh,
I'm sorry.
I'm sorry. You spoke two black holes of half the mass.
That's half the mass. That's right. Two of half the mass. Sorry, I didn't say that clearly.
Ah. Okay.
Yes.
Sorry.
Yeah.
So I think I asked you the question before. So ADS-CFT,
yes.
The idea was that we have one theory which is well defined, the other is not, and
yes.
we define one by the other.
Yes.
And now you are saying your feeling is that that's incorrect, and that actually we have to go back and define the bulk theory on its own.
I think that everyone, both pro and anti-firewall, is dealing with scenarios, not theories. The first person who with a theory wins. So.
Well, may I comment just related to this question, because in the regimes where the theory becomes non-local,
yes.
I tend to argue that these Harrison theories may play a role. And actually, if taking this point, then one can see that they affect several important issues in the story. One is that the ADS-CFT gets corrected in the sense that the boundary theory actually becomes a theory conformal gravity theory rather than just conformal theory in the standard sense.
Good.
That is a very essential issue. And another related issue is that if you look at the practical things like computations, because one is able to write some formula, it actually looks like very much like a nonlinear correction of the Schrödinger equation at the boundary. So it's maybe the same story actually kills two rabbits.
Wait, what becomes nonlinear Schrödinger equation?
Well, if you look at these unfolded equations,
yes.
they can be interpreted as Schrödinger equation actually, and then all these corrections they acquire a form of nonlinear Schrödinger equation, if you like. So, well, I'm not claiming I understand this story fully, but there is some sense of that. And actually, these nonlinear corrections that we refer to this paper about, it's pretty much of the same style. Actually, it will be operators will depend on the states, if you like, in this unfolded machinery. So maybe it's just appropriate.
So you talked about how hard you and Slava talked about how hard it was to find even the horizon so far. I mean, are there simple black holes like BTZ? Look, BTZ one sort of, I guess, has the...
Unfortunately, what I'm saying is not, I can't say much about concrete solutions. What I'm saying is a very general aspects of the whole constructions that should be explored, actually. I can't say much about...
But there are black holes for which we do have the geometry and so on.
It's not worked out yet.
Okay. Cookies.